Our next talk also has something to do with linear types. And one of the lovely things about linear types is that they're useful for so many things. And so it's my pleasure to introduce Luc Pellissier.
Exactly.
Okay. And he'll tell us about the relationship between polyadic approximations and intersection types.
Okay, so am I recorded? Sorry. Okay. So this work is about intersection types, but seen from the perspective of linear types. And actually, we carried this work with Damiano, Mazza, and Pierre Vial. And as we will show, we can view intersection types as some special simple types, but that are not given to a term, but to a linear approximation of the term. So, in order to make sense of everything, I have to introduce some words. So, first of all, I will motivate this correspondence. Then I will show a framework that is algebraic and that is general enough, abstract enough, in order to carry on the computations and the theorem provings that we want to make. I will then introduce what I'm saying, what I'm meaning by linear approximations, or not so linear approximations, actually. And then I will use everything that have been presented in order to recover intersection types. So, intersection types are some special kind of types that have been introduced in the 80s, mainly by Coppo, Dezani, Desanti. And there are type systems where a given subterm of a term can be typed many times, not necessarily only once. So you can view it here in the example that I show, which is a system which have been given in two different variants, first by Gardner in the 90s and then by Carvalho in the middle of the first decade of the 21st century actually, where we can see in the application rule that in order to type a T applied to U, you can type U an arbitrary number of times, so here with different type A1 to AN, but in order for the application to be correct, you have to type the term T with different types, all the types that are used for U. So here T is an arrow type with many types on the left and only one type on the right. And so they're used to characterize normalization properties, so different kind of normalization, strong normalization, weak normalization. And they're also used to certify reduction strategies, by which I mean that they are used to prove that certain strategies give the normal form for a certain definition of normal form. So, for instance, a derivation that is not possible with simple type, but which is possible with intersection types, is this one, which types lambda x xx, which is not typable with simple types. So these are intersection types. They are very well known, very used. On the other hand, we have linear approximations. So linear approximations come from Jean-Yves Girard's work on linear logic, and they allow to understand the reuse of variables. So they kind of gained scope with differential linear logic in 2006, I believe, by Erard and Regnier. And the idea of linear approximations is to, instead of studying a term which can have an arbitrarily complicated dynamic, to study the dynamics of its approximations, which live in a linearized language, so where the dynamics is much simpler. And so to a term here, which are written in a capital case, we associate some of its approximants, which are written in lowercase. So, for instance, if we have a term t that approximates a term m here, and t uses many variables that all approximate the same variable x, we can say that t abstracted with all these variables approximates m abstracted by x. And the same thing for application. So these are systems that have been used in different settings, but if you just watch it a bit carefully and remember the systems that I showed before, it seems tempting to try to superpose them. And indeed, it is possible. So here I just rewrote the same rules, In black, what is in all the systems, so the lambda calculus part of the system. In blue, the types. In green, the approximations. And indeed, it seems striking that in a way, what we are doing when we are using intersection types is, in a way, typing the approximations. Indeed, the rules completely superpose. So this is a striking correspondence, and it seems interesting to try and understand it. But there is first problem when you try to understand it, is that there exist many flavors of intersection types. So indeed, there exist intersection types for many languages, for call-by-name lambda calculus, but also for call-by-value lambda calculus, for lambda mu calculus, so it has to encompass some classical features for classical logic. But not only are intersection types used for many languages, but they are used in many variants. So for instance, there are intersection types that are idempotent. So the intersection of a type with itself is the same thing as the type. But there are some that are not. There are some intersection types that are rigid. It's impossible to commute. But there are some that are not. The same thing with relevance, etc. Also, intersection types are used to characterize different properties of normalization. Strong normalization, weak normalization, add normalization, you call it. So there's a need for an abstract framework, which causes us to move up the ladder of abstraction. Yeah. So indeed, we need an algebraic framework for calculi. So this algebraic framework is higher categories. So I'm sorry about it. So we will represent calculi as cat operas. So what's a cat opera? It's category-like structures with objects, multi-arrows between objects. So what's a multi-arrow? It's exactly like an arrow, but it has multiple inputs and only one output. So multi-arrows are terms with their free variables as inputs. Composition is substitution, well, if you will. And the two arrows, so in a cat opera, there are also two arrows between the multi-arrows. And so if you think of it as a calculus, the objects are just types. The multi-arrows are just terms with their free variables. And the two arrows are reduction path. So for instance, we can consider as a cat opera the untyped lambda calculus. It only has one object, the absence of type. Multimorphisms are just terms with fixed free variables. And, well, composition is substitution. And a two-morphism is just a reduction path. So all of the lambda calculus, its types, which in this case is known, its terms and also its operational semantics are completely encompassed into the cat opera presented here. In the same way, we can give a cat opera for something typed, such as minimal natural deduction. And so we give here a same cat opera, where here the multi-arrows are natural deduction proofs. We know, at least from the 1930s and the Göttingen school, that not only are objects in mathematics interesting, but also morphism between them. And so morphisms of cat operas also get great interpretation in that case. And so we can view morphisms of cat operas, so morphisms that preserve all the operations that are endowed in cat operas, can be interpreted either as a translation, so which is the fairly most natural meaning of morphism, but it can also be interpreted as a semantics, which is not that different from a translation. But more interestingly, for our purpose, it can also be interpreted as a type system. So this is an idea that was presented 3 years ago at POPL', I think, that has been introduced by Melliès and Zeilberger. And it is about viewing a morphism, in their case of category, in our case of cat operas, from a certain cat opera C to a cat opera B as a type system for B. The main idea being that C is viewed as a category of derivations and B as a category of untyped terms. And so we view one of these morphisms as a type system if and only if it enjoys a certain fibration-like properties that ensures that the reductions have the same structures when they're viewed typed and untyped. So we can put everything in the same diagram. So type systems, such as, for instance, the Carrier isomorphism between natural deduction and the lambda calculus, untyped lambda calculus. But then we can also draw on the same diagram a translation. For instance, lambda calculus can be translated into a certain language for linear logic, which is what I write lambda bang, which can in itself be translated in a bigger language for linear logic, which is classical, which is the linear logic proof net, MEL. And then we can view also on the same diagram a semantics for MEL, which, for instance, here is the relational semantics for linear logic. So everything gets completely homogeneous. Okay, so then we can introduce linear approximations. So in a language such as a language for linear logic, we have an explicit repetition modality, bang. And we decide that a term with an explicit repetition modality has to be approximated by many terms, so a sequence, a list of terms. And so, for instance, M applied to bang N is approximated by an approximation of M, T, applied to a sequence of approximation of N. It's also very important that we also approximate reductions. So we can give a system here. I won't delve into details, but what's important is that we can put or not the structural rules in order to have many different flavors of calculus. And indeed, contrarily to what I kind of said, we are not talking about linear approximation, but something way bigger. We can decide to be linear or decide not to be linear. Once we have chosen to be linear or not, it is fairly easy to see that the system we gave defined an approximation pre-sheaf, which is just another way of speaking about approximations. The main thing to understand is the second rule, the second bullet, which is that we associate to a term its set of approximations, parameterized by the types, but just really something simple. And also we associate to every reduction the set of reduction that the relation of terms and its reducts that follow the reduction. So all of the notion, what was important in this formulation as an approximation pre-sheaf is that also the notion of approximation gets completely homogeneous to everything else, to type system, to things like that. It's just a certain morphism of ket operator. And it will be very important in order to recover intersection types. The main technical tool in order to recover intersection types is the Grothendieck construction. So the Grothendieck construction, adapted to our setting, gives an equivalence between approximation pre-sheaves, that is the things that I presented, morphisms of ket operad into dist. I won't delve into details in what is dist, but nonetheless, it exists. And type systems for B, which means that we have two views on type systems, either as some sort of forgetful functors that maps to a derivation a term, or either as something that maps to a term its set of derivations. And indeed, if we apply this machinery to the examples that I gave before, it indeed yields a correspondence between the two systems that I showed at the beginning. Different notions that we love, such as subject reduction and subject expansion, can be recast in the language either of type systems or as pre-sheaves. And it's really important to have both, because this is how we prove that certain intersection type system characterize normalization properties. So subject reduction is the fact that the type is preserved along the reduction, and it translates as a sort of an up fibration-like property. And in the same way, it translates viewed as a pre-sheaf as a property of entirety. The fact that the relation that I showed before is entire and completely dual for subject expansion. So now the work is finally set to show you the main theorems that we dub the fundamental theorem of intersection type. So in the same way that there is a fundamental theorem of analysis or fundamental theorem of algebra, which is not that interesting, but that exists. we have the fundamental theorem of intersection types. So, how do we read it? Every time we have a language, L, that can be translated into linear logic in a meaningful way, and every time we choose a way of approximating linear logic, that is, by putting more or less structural rules in it, we have a notion of approximation for our language. And so our language is approximated by the approximation presheaf, which is this composite functor. And if this presheaf has certain properties of entirety relatively to a family of reduction and of surjectivity relatively to a strategy, which are some parametric things that we can choose to decide on or not to include, then we have the chain of implication. That is, T is weakly normal relatively to a strategy RW. What do we mean by weakly normal? Just that if I only follow the strategy RW, T ends on a normal form. So if T is weakly normal, then T is typable. And if T is typable, then T is strongly normal relatively to the other family of reduction, which means that when I choose any reduction inside RS, T terminates. And so we view in this diagram that we don't bridge the last implication, and so RS and RW have to be chosen in a way that makes possible the last implication to be true. But, well, this seems pretty normal to have something that is called strongly to be stronger than something that's called weakly. So this sounds great. And so, indeed, we view that, in a way, intersection types here allow us to go in the other direction, go from some weak notion to a strong notion. And so, in a way, this distills the essence of intersection types to bridge a certain gap in some situations between being weakly normal and being strongly normal. And, well, this theorem is useful because it allows to recover usual intersection type systems together with their normalization theorems and the strategies that are well known to be complete for them. So we can recover, when applied to the lambda calculus translated into Mel by the Girard translation, and using an idempotent polyadic calculus, we recover Coppo and Dezani's original intersection type system. When we use a non-idempotent one, we get the Carvalho system R. When we translate the lambda mu calculus into linear logic proof nets, we get Kestner and Vial's system for the lambda mu calculus. And we get, together with that, their theorem of normalization. So we characterize their normalization by the system we defined. So all of these proofs of adequacy between an intersection type system and a certain normalization get factored. And actually, we see that they are all easy consequences, well, easy, modulo the theorem of the fundamental theorem of intersection types. But they are all consequences of the fact that multiplicative and exponential linear logic, propositional multiplicative and exponential linear logic, is strongly normal. So everything gets condensed in one result that have been known for 30 years. So as a conclusion, you can see that we gave a very general, very abstract framework, maybe a bit too much abstract, that can express calculi, that can express relations between calculi, but that allows to say one slogan, and that allows it to be fully, precisely true, which is that intersection types are simply typed approximations. And also we view that all the normalization proofs of the systems we were interested in are indeed corollaries of the normalization of linear logic, which was not very obvious at the beginning, but which gets completely clear here. Thank you.
Okay, so do we have any questions? And if you're feeling shy, there's also this Slido thing that Ranjit wants us to use.
Yep. So if I understand correctly, your system is somehow perceived-based. Is there any relevant story for the handling of positive data types in your system? Like, it's quite well known that if you do some Kripke models, the completeness for Kripke model is broken with positive data types. Do you actually encounter the same kind of limitation?
I absolutely don't know. There might be, but I didn't look into it, and yeah, but we can take it offline.
Do we have any other questions?
So why do you need to work with cat operands? Why can't you work with the two category of context instead?
There's a bit of it which is just an aesthetic decision to work with multimorphism instead of just morphisms. It is not that useful. Well, yeah, okay. It is useful for one thing, which is to be able to speak about classical calculi. Classical calculi needs the ability to swap one conclusion swap the conclusion for one of the hypotheses. And they don't, well, this operation feels very natural in an operatic setting. Actually, it has been studied in algebraic geometry under the name cyclic operas for quite a long time. And it doesn't feel that natural in the context of a category of context. So it's really for the extension to the classical setting that it's needed.
Any more questions? Okay, we have one question from online, and I'll tell it in here. So sorry, I'm shouting at you, but we need to record it. So
put myself here so it's less awkward. Yeah, perfect.
Is this working? No, it's not. Okay, I'll just shout, and then maybe the camera will pick it up. So the question was, do some types work because they have different typed eta expansions? They have extra typed eta expansions. Yeah. So the question was, do some types work when in this framework?
Oh, some types.
Yeah.
Well, depends on what you call working. But for instance, some properties of yeah. So okay. So in all what I presented, the fact that you decide to choose to put inside eta expansion or eta reduction or whatever inside your system is in a way can be put inside this framework by choosing different two arrows. And so if I work with a system where eta expansion fails, for instance, sudden types, it will be present at the level of cat operands with some 2 hours that are missing. And so, yes, it will work, but it will maybe be useless or anything.
Any more questions? Okay, then let's all thank the speaker.